A presentation on heat treatment of steel, in which the subtopics we are going to deal are normalizing, hardening, tempering, this process, and TTT curve along with CCT curve, os tempering and Mott tempering process. So myself, M.Kiran Kumar, M.Tech, CL Mechanical Department, Government Polytechnic Kataram. The topics to be covered are, again, we are repeating them. So the normalizing process, the difference between annealing and normalizing process, then hardening process, tempering process, along with the TTT curve and the CCT curve, along with os tempering and Mott tempering process. So initially we are starting with normalizing process. Coming to the normalizing process, it is a process of heating the steel up to the above upper critical temperature, nothing but 810 to 930 degrees centigrade, followed by cooling in still air. So the purpose of normalizing, why to normalize a metal? The main reason for normalizing is to adjust the mechanical properties to make the metal suitable for the service conditions. Not only that, the other purpose is to relieve the internal stresses, to refine the grain structure. The grain structure will be refined, the machinability property will be improved, and the toughness and strength will be improved. So those are the purposes why we are using this particular normalizing process. So in normalizing process, what happens actually? Let us see here. So a metal is heated, nothing but the steel is heated from 30 to 50 above upper critical temperature, nothing but A3 for hypoeutectoid steels and ACM for hypereutectoid steels. So here A3 ACM. So this is the normalizing temperature, and holding at this temperature for reasonable time to prevent grain growth. So in this particular diagram, we are able to see the PR light here, nothing but 0.8% hypo and hyper rectoid steels. So this is A3 temperature and ACM temperature, nothing but ACM point. So here the vertical is the temperatures and the horizontal is the carbon content. So here A3 point and ACM point are the particular critical temperatures. So the time allowed should be sufficient so that the temperature is uniform throughout the section. And then cooling in air. In air it is cooled. Then the cooling rate is the major difference between normalizing and annealing. So the microstructures produced by normalizing is slightly different that of annealing. So what does the difference mean? So the microstructure will be differing from the normalized steel and annealed steel. So, but slightly more cooling results in final grain structure than annealing. So the normalized steel is slightly coarse compared with the annealed steel. But even if you slightly cool more and more, then it results in finer grain structure. Next, the normalized structure of low alloy steel consists of sorbite. The sorbite is fine perlite, and the low alloy steel consists of sorbite and fine ferrite, nothing but fine perlite and fine ferrite. So The increased rate of cooling in normalizing results in high hardness and low ductility than the annealed steel. So this is the difference in the case of hardness and ductility from annealing process or annealed steel. So the effect of increased rate of cooling also increases strength and toughness of the steel. So normalizing is widely used in industry because it is more economical than annealing process. So normalizing process is usually performed after cooling, forging or casting for grain refinement especially. So in forging or casting for grain refinement, this particular normalizing process is performed, and the normalizing temperature generally varies from 810 to 930 degrees centigrade. So you can say that for a grain refinement of steel by forging or casting, we need to normalize it at from 810 to 930 degrees centigrade. We need to heat it, hold it for some time, and then cool it. So coming to the normalizing diagram, we have already studied. This is the ACM, this is A3 critical temperatures, and this is the normalized, and this is the austenite. These are the temperatures, and this is the carbon content. Here it is ferrite plus perlite, and perlite plus cementite. This is the perlite. Ferrite plus austenite, cementite plus austenite, and this is 910 degrees centigrade, and this is 1130 degrees centigrade. So let us look at the differences between the annealing and normalizing process by categorizing them by different factors. So the first one is by temperature range. This is annealing and this is normalizing. First factor or criteria is 30 to 50 degrees centigrade above A3 for hypoeutectoid steel, the same amount above A1 for hypereutectoid steel in the case of annealing. Whereas compared with normalizing, it is 30 to 50 degrees centigrade above upper critical points A3 for hypotectoid and ACM for hypereutectoid steels. That is the difference. Second criteria is what is the method of cooling used in both methods. In annealing, within a furnace, the steel is cooled, so that is slow rate of cooling. Whereas in normalizing, it is cooled in air, faster rate of cooling is achieved. Coming to the third criteria, grain structure. In annealing, coarse grains are obtained, whereas in normalizing, fine grains are obtained. Coming to the fourth criteria, properties. Annealed steel possesses high ductility and low hardness, whereas normalized steels possess high strength, hardness, and toughness. Coming to the cost criteria, takes costly furnace and time. It is cheaper, components spend less time in furnace. Now we are moving to the hardening process. So the hardening, what is hardening? As the name indicates, making a steel harden. Hardening may be defined as the process of heating the steel to austenite phase, followed by rapid cooling in a liquid bath such as water or oil. So heating it up to the austenite phase and then rapid cool it by a liquid bath such as water or oil. So this is hardening process. And what is the purpose of hardening? So to develop high hardness and wear resistance to steels, we use this particular hardening process. So to improve the ability to cut over other materials, nothing but to make cutting tools. To make cutting tools, hardened steels are used. So we commonly see HSS, high speed steels for cutting materials, and not only that, tool steel, hardened steels, etc. HSS are commonly used for cutting tools. So to improve the ability to cut the other materials. Next, to improve strength and toughness of steels. So let us, after studying the purposes, now let us move to the actual what is the hardening process. So heating the steel to a temperature from 30 to 50 degrees centigrade above A3 point for hypoelectric steels and 30 to 50 degrees centigrade above 1A13 point for hypereutectoid steels. This is A3 and this is A13. So those are the temperatures. Heating the steel up to that particular temperatures and holding at this temperature for a considerable time to complete phase transformation, and then sudden cooling in water or oil. So that is the difference between the normalizing and annealing and hardening process. So the sudden cooling, not slow cooling, as compared with annealing and normalizing process. So we can see the same diagram. So this is our hardening process. This is the austenite and this is ACM. So these are the carbon contents and this is the temperature. So coming to the process of hardening. So carbon steels are usually quenched in water. So quenching is sudden cooling. After heating, if we suddenly cool a steel, that is known as quenching. Steel or any other metal, if we after heating, if we suddenly cool it, then that is known as quenching. So alloy steels are quenched in oil. Sudden cooling is called quenching. Quenching in non-equilibrium process and cooling rate is greater than or equal to critical rate. So therefore, the martensite structure obtained in cooling is not predicted in phase diagram. So after quenching, the hypoeutectoid steels has fine-grained martensitic structure. So the structure of hypereutectoid steel consists of martensite embedded with carbon network. So the structure is harder than the martensic structure of hypoeutectoid steels because cementite crystals are harder than martensite crystal. So overall, we can say that uh, the structure, the hypereutectoid steel structure is harder than the Martin structure of hypoeutectoid because cementite crystals are harder than martensite crystals. So the mechanical properties produced as a result of hardening process followed by tempering depending upon the carbon content and the rate of cooling and tempering temperature. So three factors we are discussing: carbon content, rate of cooling and tempering temperature. So next topic we are going to discuss is salient points of hardening. Steels with low carbon up to 0.3 percentage will not respond to hardening process. Steels with low carbon content, that is up to 0.3 percentage, not have any response to hardening process. The hardness increases with the carbon content. So above 0.6 percentage of carbon, the hardness cannot increase appreciably. To obtain martensitic structure, the cooling rate should be higher than the critical rate. To obtain martensitic structure, the cooling rate should be higher than the critical rate. So increasing the temperature of tempering results in decreasing the hardness of steel. So increasing the tempering temperature decreases the hardness of steel. Then hardening is applied to cutting tools and machine parts where high hardness and where resistance is required or desirable. So this is the hardening process. Just now we have discussed the same diagram. So now let us see some of the points why the structure of steel after hardening is not suitable for industrial applications. So the reasons are the martensite, the first reason, martensite obtained due to quenching is extremely brittle and not stable. So the martensite obtained by quenching is not stable because it is brittle. And quenching produce high internal stresses in the hardened steel, which results in distortion and cracking of the part while in service. So quenching may cause distortions and develop high internal stresses, and the parts may have the cracks or a break during the regular service. These unfavorable characteristics are eliminated by subsequent heat treatment called tempering. So soon after hardening, tempering process should be performed. So the tempering, what is tempering process? So tempering is a process of heating the hardened steel to a temperature below lower critical temperature, followed by slow cooling. Nothing but heating the hardened steel below lower critical temperature, followed by slow cooling. So the tempering renders the steel tough and ductile. Nothing but tempering enables the steel to be tough and ductile. Nothing but the ductility property will be ductility, the steel will be having the ductility property. Next, what is the purpose of tempering? We have discussed the reasons. Hardening increases the strength, hardness in the steel, but decreases ductility and toughness. That is, imparts brittleness. So in order to reduce this particular brittleness, we are using tempering process. So the steel under high hardened condition also, to relieve the brittleness, tempering process should be performed. So the main purposes of tempering are to reduce the thermal stresses, stresses caused with the temperature and effects, to stabilize the structure of the metal, to reduce the brittleness, to increase the toughness and ductility. This particular tempering process involves heating the hardened steel below lower critical temperature, holding the steel at a particular temperature for the sufficient time, and slowly cooling, not sudden cooling. It is a slow cooling process. So the tempering temperature must not exceed the critical point. So the coming to the hardening process, the steel heated to about critical temperature become austenite, and the the benefits of hardening treatment would be lost. Nothing but because of that we are performing the tempering operation. So the temperatures are related to the function of components. Cutting tools are tempered between 230 to 300 degrees centigrade. Nothing but if you want to harden a particular steel, and in order to use that steel for cutting tools, we require to, after hardening, we require tempering, that is 230 to 300 degrees centigrade tempering temperature. If greater ductility and toughness are required, as in case of shafts, high strength bolts, etc., the tempered temperature should be 300 to 600 degrees centigrade temperature. Tempering causes transformation of martensite into trostite or sorbite. We already discussed what is martensite, trostite, and sorbite. So formation of these structures depend upon the temperature. So these particular structures consisting of ferrite, finely divided cementite, and are different from those produced by slow cooling. So nothing but by hardening process, whatever we harden a particular steel, those iron components, nothing but the steel, will be different from the products hardened or the products made by slow cooling. Nothing but the change of structure due to hardening and temperature. Let us see in this particular diagram. So here, this is martensite structure, this is sorbite, and this is austenite. So quenching process, because of quenching and tempering. Quenching is sudden cooling, and the tempering is the required tempering temperature depends upon metal to metal. So that is 550 degrees centigrade. So now let us move to the different temperatures. Low temperature tempering, medium temperature tempering, and high temperature tempering. So let us see what is low temperature tempering. That is heating the steel from 150 to 250 degrees centigrade. So the purpose of low temperature tempering is to relieve internal stresses, to increase the ductility without changing the structure. The process performed at 150 to 250 degrees centigrade as given. So the tempered component cannot carry dynamic loads. The process is applied to cutting tools, and this is the diagram. This is the low temperature tempering process is performed at this particular temperature. That is 150 to 250. So here 150, this is 200, and this is 250 degrees centigrade. So this is low temperature tempering process performed in between this range. So next is medium temperature tempering. Coming to the medium temperature tempering, temperature is from 350 to 450 degrees centigrade. So the hardened steel is heated between the temperature range of 350 to 450 degrees centigrade, and after heating, the martensite structure changes to trostite structure. As a result, change in the structure of the steels become nothing but the steel will be much more tough and ductile. The hardness is considerably reduced. So the process is most useful in case where strength reliability are important than the extreme hardness. So medium temperature tempering is most commonly employed for coils, laminated springs. So here, this is the temperature range of medium temperature tempering. So that is 350 to 450 degrees centigrade. This is 350, this is 400, and this is 450 degrees centigrade. Medium temperature tempering process range. Next is high temperature tempering process, where the temperature range is 500 to 650 degrees centigrade. So here the steel is heated up to from 500 to 650 degrees centigrade, and where martensite is transformed to sorbite, internal stresses are eliminated or totally relieved, and the toughness is improved by high temperature tempering process since we are increasing the temperature. So sorbic steels are softer and more ductile than trostic steels, that is of medium temperature tempering process. Sorbite and trostite are usually known as tempered martensite. High temperature tempering is applied for gear, wheels, axles, shafts, and connecting rods in automobile sector. So here, this is the 500, 550, 600, 650 high temperature tempering range. So here, uh, till now we have studied uh, tempering, hardening process. So now let us move to the curves, which are very important concerning the engineering materials, known as first one is TTT curve. So triple T curve, the full form is temperature, time and transformation curve. So temperature, time and transformation curve. The temperature and the time, the transformation from one phase to other phase occurs. So that is the TTT curve. The decomposition of austenite under non-equilibrium conditions is obtained from TTT diagram. So the TTT diagram relates the transformation of austenite to the time and the temperature conditions. So this diagram for steel clearly explains the decomposition of austenite. So the other names for this particular triple T diagram are S curve and C curve. So now let us see the triple T curves, TTT curves for eutectoid composition. So here, this is the time on the horizontal and vertical along x-axis time in seconds, and on y-axis temperature in degrees centigrade. So the time is given in 1, 10, 100, 1000, 10,000 and 1 lakh seconds. Whereas the temperature is given in minus 100, 0, 100, 200 up to 700, 723, maximum 800 degrees centigrade. So now from different times, the temperature, how the transformation begins and how the transformation ends, those are given. So here, coming to this transformation begin, so it is perlite, then sorbite, this is prostite, and this is bainite. And here the unstable austenite and austenite plus martensite, here this is martensite. So let us have a look about this particular diagram. Triple T curves are drawn by taking number of steel specimens. Each specimen is heated to austenitic temperature and then quenched to predetermined temperature. So each and every specimen is to be heated to austenitic temperature and quenched for determining for a particular temperature. So the transformation of austenite begins at a particular after certain time known as incubation period. So the waiting period is known as incubation period. So in triple T curve, the points AS and AF represents the beginning and ending of austenitic decomposition. AS and AF. So these are the beginning and the ending of the transformation. So in triple T curve, as we are discussing, AS and AF represent the beginning and ending of austenitic decomposition at 700 degrees centigrade. And as we have discussed, so the decomposition of austenite will be at 600 and 400 BS, BF and CSCF respectively. So BS and BS to BF 600 degrees centigrade and CSCF 400 degrees centigrade, that is the austenite decomposition. So the curves 1 and 2 are drawn through all the points indicating the beginning and ending of austenitic transformation. Curve 1 and curve 2. Curve 1 represents austenite beginning to decompose. Curve 2 decides the austenite decomposition is completed. So the interval between two curves indicates the condition for the partial decomposition of austenite into ferrite and cementite. So the triple T diagrams are useful in heat treatment as they give the nature of transform product of austenite at varying degree of cooling, nothing but different at different cooling degrees or cooling rates. How the transformation occurs are shown by the triple T curves. Whenever the transformation takes place isothermally, transformation of austenite takes place isothermally, then only triple T curve is said to be valid curve. So that was a triple T curve. Now let us move to the CCT curve, that is continuous cooling transformation curve. So the CCT curve correlates the transformation, temperature and time during the continuous cooling process. So CCT curve is a continuous cooling transformation curve which correlates transformation, temperature and time during continuous cooling. So CCT curves are drawn similar as TTT curves, but continuous cooling from austenite zone to room temperature, that is achieved. So here we are able to see the CCT curves. So here, this is the indication of CCT curves. And this is TT curve. These are the TT curves. Time and temperature curves. So at the A point, furnace cooling, where coarse perlite is obtained, and the B, air cooling, fine perlite. C, this is oil cooling. D is critical rate of cooling, and E is cooling in water. So there is a comparison of CCT and TT curves, TTT curves. So coming to the CCT curves, the point of starting and the ending of austenite transformation are recorded on the continuous cooling curve as shown in the figure. So here, this is the CCT curve. So starting point as well as ending of austenite transformation are recorded. That is the cooling curve, and in hardening process of steel, CCT curve is followed. Now let us move to the Ost tempering process. So here we are discussing the Ost tempering process. So coming to the Ost tempering process, the steel part is heated to the hardening temperature range. After heating to the hardening temperature range, then it is quenched down to a temperature of 300 degrees centigrade. After hardening temperature, then it is quenched down to 300 degrees centigrade, and it is held there for sufficient time to decompose austenite into bayanite. So austenite decomposes to bayanite after waiting at a particular time. sufficient time at 300 degrees centigrade quenching. Then it is cooled to room temperature. So this is austenite, and here is the transformation start and this is the transformation end. It's austenite decomposing to bainite. So the schematic representation is already given here. This is the cooling curve for austenite process. This is austenite. This is bainite, which decomposes and forms bainite. This is the transformation starting curve and this is the transformation ending curve. So the hardness and strength of the austempered steels are nearly same as conventional hardened tempered steels. Nothing but the tempered steels have the same properties like hardness and strength of the austempered steels. But the difference is the ductility and impact strength, usually higher for austempered steel compared with the tempered steel. Only the difference is ductility and impact strength are higher for austempered steels compared with tempered steels. And austempering is applicable only to small sized components made up of high carbon steels or low alloy steels. That is austempering process. Now let us move to the mark tempering process. Coming to the mark tempering process, it is the hardening process with minimum distortion and residual stresses. So coming to the process, what happens here is in mark tempering process, the steel is heated to hardening temperature, then cooled suddenly above the critical rate of cooling down to a temperature just above MS point. Temperature at which martensite formation begins is nearly equal to 250 to 40 degrees centigrade. And so here we can see here transformation starts and transformation ends, and this is austenite to martensite. And after heating, it is held for a sufficient time to attain uniform temperature throughout the section. And then short now decomposition of austenite into bainite. And then from above MS point, it is cooled in air. The martensitic transformation takes place under lower cooling rate, and hence internal stresses are reduced to a greater extent. Nothing but internal stresses are relieved to a greater extent. So this method can be used for heavy sections and pieces of irregular shapes. Compared with the austempering process, mark tempering can be used for heavy sections and irregular shapes. So with this, we are completing this particular presentation. As we have listed, we have completed all the topics, but let us have a small summary of all the topics covered. So initially we have started with the normalizing process, heating the steel above upper critical temperature 810 to 930 degrees centigrade, followed by cooling in still air. So that is known as normalizing process. So we have studied purposes of normalizing like grain refinement, relieving stresses, etc. So this is the diagram we have discussed for normalizing. This is the normalizing diagram. So later we have entered into the several factors for normalizing process. Later we have discussed the differences between annealing and normalizing process with the temperature range, method of cooling, grain structure, properties and cost. Later move to the hardening process. What is hardening process we have discussed and the purposes and the diagram concerned with the hardening process and the process of hardening. What happens in hardening we have discussed. Later moved on to the salient points of hardening process. And next entered into the tempering and its purposes. So after hardening, why the tempering is required we have discussed. Next moved on to the change of structure due to hardening and tempering, and moved to the different tempering process like low temperature tempering, medium temperature tempering, and high temperature tempering process in detail. Later move to the TTT, triple T curve, time, temperature and transformation curve, and CCT curve, continuous cooling and transformation curve. Latter entered to the other two topics known as Aus tempering and Mart tempering process. So with this, we are completing the total topics in this particular presentation. Thank you.